as the screen is warming up here, does anybody have any questions from last lecture? All right, so let me to review really quickly while it's warming up. So basically what we went over last lecture was this idea that in order to perform every operation in an advanced digital system, we have to work on what is an arithmetic logic unit. So we talked briefly about input registers and control values, and that we have these flags. And today we're going to talk about floating point addition. One of the flags that we're going to take advantage of is this concept of overflow. We talked about the limited range when you have a reduced instruction set computer, where that range goes through from 2 to 31 minus 1 to negative 2 to 31. We talked about the most significant bits. We talked about overflow. So this is going to be a concept that's going to become important today when we're just discussing when overflow is possible and when it's not. You're adding two values of the same sign. You can get overflow, but if you're doing addition where there are two different signs, you cannot get overflow. Then we went into some problems we just briefly described exceptions. And then talked about IEEE 754 format. We gave a couple examples of how do we actually convert this exponent value, the mantissa value, and the sign bit to be able to actually obtain a number greater than 2 to the 31. And here we just gave a couple of examples where it's actually coming out to negative infinity, and here we actually were able to get the exact value of 84. And so we talked briefly about what is actually physically an addition doing. We reviewed the concept of sign and carry out. We discussed how do you actually do addition and subtraction by performing 2's complement using a bunch of XOR gates instead of actually having to have another set of full subtractors. So you're able to perform the same thing with improved performance in less area with no design trade-off. So this is an example of when some good design benefits you. We also talked about ripple carry adders, how to speed up the adder using carry select adders, and then we briefly discussed this idea of how fast they actually go. So today what we're going to start talking about is the idea of a fully multifunctional ALU, and then we're going to go into how you actually perform floating point addition, and then we're going to go into multiplication, and we're going to go into two types of division algorithms. So the whole point is, if you recall from your adder where you have values carrying in, where you have your full adder, full adder, full adder. So in the arithmetic logic unit, what you're going to do is you're actually going to have each 1-bit operation within these cells. So you're going to have a cell coming in, and then you're going to have your multiplexer decide the result based on the control signal. So what's actually going on here is the ALU simultaneously is performing all of the operations based on what's being put in. And the control values are actually telling you which one that I actually want. So in this specific case, this is a small ALU that performs addition and has NOR, OR, and operations. So I want to perform a 32-bit AND, or NOR operation. I can perform that with this arithmetic logic unit. So what ends up happening is the control signal comes in from your opcode and indicates which one I want. So this would be a 2-bit operation. Now, one thing I should point out, and we'll get into this much more detail. This notation here, does anybody know what that notation means? What's that? Okay, so it's a bus. That means that there's more than 1 bit here. Now, typically what you'll see, and so this is kind of a poorly notated figure from the textbook, but what you'll typically see is that value and the number of bits on the bus. So that way you can actually look it up. So when you get to the data path, there's going to be values we're going to indicate, okay, so in order to go to the multiplexer, I need 5, and I have 2 5-bit values coming in. I have a 0 and 1, I have a control signal, and on the output, I have another 5-bit value. So it's a 10 to 5 multiplexer. This becomes important, especially when you're doing advanced digital design, how you keep track of where all your buses are going, what signals you can put on, and why. So in this case, this is going to be a 2-bit operation because we need 2 bits to differentiate between 0, 1, 2, and 3. So if it's 0, 0, comes in on off, it gives me AND value on the output. If it's 0, 1, I get the OR value on the output. If it's 1, 0, I get NOR on the output. If it's 1, 1, I get full adder on the output. And then what ends up happening is each bit's going to calculate and then go to the result. So there's other things that they're going to be doing with the arithmetic logic unit besides just doing ALU, besides just doing full adders or AND and OR. Sometimes we're going to be doing something called comparison. And this is going to become very important when we get into branching and jumping. So what this is this is a circuit that performs A is less than B, A is equal to B, or A is greater than B. So I want all of these values on the output because I'm going to need these to be able to perform certain calculations. For example, if I is less than or equal to J, what's going to end up happening is we're going to perform 2 operations that tell us specifically how to do this. First, is I less than J? No. All right. Well, then I find out that then I got to do greater than or equal to at that point. And so these circuits allow me to do this. So in this case, and I'm going to zoom in here so you guys can see it, A is less than B is actually equal to A not B. So if I have A and B, if I have 0, 0, 0, 1, 1, 0, and 1, 1. So I'm comparing these 2 values, right? So the output F, so what's going on here? So if it's 0, 0, they're the same, right? So we want an equal sign. If it's 0, 1, this means B is greater than A. If it's 1, 0, this means A is greater than B. And 1, 1 means that we're equal again. So what this circuit is actually doing is telling me that I want A not B here, right? So in this case, A not B. So I've inverted the A value and B into an AND gate, and that gives me C equals not A and B, which means that I have A less than B, right? In the case of A greater than B, I want the B inverted because you can see here B is 0 and A is 1. So B is inverted, the A value goes onto the input here, and the AND of that value tells me A not B, which means that A is greater than B in this case. Does that make sense so far? So what ends up happening here is that we can simply reduce this by saying an OR gate, by using a NOR gate. So if this value is 1, that means they can't be equal, right? If this value is 1, that means they can't be equal. Does that make sense? So basically what we're doing is we're just using a NAND gate here, NOR gate here, that if both of these are 0, then I get a 1 on the output. So that just reduces to the negation of not A and B or A, B not, which then comes out to just simply A equals B. Does that make sense? Going look a little confused. That's how you trying to figure it out too. Does anybody have? Feel free to ask questions. I'm not going to shout you down and tell you that you're being stupid. And so, this is not going to be a TGO or a type of question, but this is an example of how do you take these 2-bit comparators and put them together. So you're actually kind of working from the most significant bit down and trying to solve it. So what ends up happening is if you have a series of bits where you're getting 0, right? So we're comparing these 2 numbers, right? We're trying to figure out which one's is A greater than B. So they're the same, and then we get to the first possible bit that we can actually differentiate between. That allows us to just say, all right, we're good here. Now, if we had a 1 here, that would allow us to just say, oh, we're done. We don't need to perform all these other calculations. So it's a cascading thing, kind of like addition that we discussed earlier in subtraction. So what we want to be able, so this is actually a description for those of you who remember K-maps and reduction of logic. How do you actually design this 2-bit comparative? Well, you just do all of the operations. You figure out what your K-maps are, reduce the logic, and then the actual circuit is TGO 2.12, which is just a 2-bit comparator. Well, in this case, we perform this logic reduction, and you have A1 and A0 are your inputs, B1 and B0 are your inputs. So you're doing a 2-bit comparator. So we are allowing A to be our first register and B to be our second register. So basically what's telling us is that A is greater than B, A is less than B, or A is equal to B. And that's important. If you recall what I was talking about in the first lecture about you have to worry about what the coder tells you, this is a great example of what this is. So basically, if I is equal to j, if the coder puts in the j value for I and the I value for j, well, there's not much you can do about that. You've done everything that you're supposed to do. You can't. You can only do so much. So in this case, we show that we've done the logic reduction. If you don't mind, I'm going to scroll up here just for a moment so you can see how the K-map worked. And the result is we were actually able to reduce the logic here, and then from there we're able to just design the K-maps to give us the smallest possible output combination. So in this case, A equal to B is just equal to these XOR values, right? XOR and XOR of A1 and B1, or A0 and B0, right? And then those values, if you get an OR on the output, that's going to give you A equals B. In this case, if you're going to have A1 and A0, then B1 and B0 are negated here, and these go into your different logic values, right? See how that makes sense? So then that's actually performing the calculation and doing this forward. So then what ends up happening is that you're performing 3 different ANDs. You're getting A1 and B1 not. In this case, it's A0, B1 not, B0 not. In this case, it's A1, A0, B0 not. So from there, if any of those are 1, that means that A is going to be less than or greater than B. So what ends up happening is that if you're trying to make a 32-bit comparator, it can get pretty complicated if you're trying to reduce the logic here. So in this case, this is actually going to require fewer gates than if you just made the 1-bit and 1-bit and made it cascade. So it's a reduced logic. However, it requires more design complexity. You require more design complexity at the design automation stage. You also have to do far more complex K-maps. So eventually at some point, you can just go, how much performance and area trade-off do I really need in design complexity trade-off? Yes? Sure. Which one?
At the end, right before A equals B.
Oh, A equals B? Yeah, that's an AND. Yeah. Oh, I'm sorry, that's an, wow, that's a terribly drawn OR gate. Doesn't, let me be clear. OR.
And then this bottom 3.
These are AND gates, and that's an OR gate. Here, I'll put A, excuse me. I'll just put O, A, and O. And this is no. And this is X for XOR and XOR. So does anybody have any questions about this specifically, how does the trade-off between reducing the area and design complexity come into play? All right, so I'm going to scroll up a little bit and start discussing the actual layout of arithmetic logic unit. So in MIPS, so TGO 2.13 also includes the drawing. So I want you to actually draw this ALU operation. So the inputs to the MIPS arithmetic logic unit are two 32-bit values. Remember, everything in a reduced instruction set computer is going to be the same. The size of the memory, the size of our buses, and the size of the inputs to the ALU, the size of the instructions, all 32 bits. So the two inputs to the MIPS ALU are two 32-bit values, A and B, and a 4-bit control signal. So if I have a 4-bit control signal, how many different operations can I use? I heard it. Page correct, 16. It's 16 because of 2 to the 4, right? The outputs are the 32-bit result, which is ALU out, a 0-bit used for comparison between branch equivalent and branch non-equivalent. We'll get into more detail what that means later. Well, basically what it's doing is it's performing a comparison, and then the moment you actually get a comparison, you're getting a result. So the 0-bit is either going to be, you can actually perform an operation that tells you whether or not an addition or subtraction gives you a result of 0, or if the 0-bit actually has a 1 on this output, you actually know that there's some sort of branch element required. So this is a reduced design where we're actually figuring out, okay, the value that we want for 1 on the 0-bit also means that we know that we need to branch in a specific operation. And we'll get into a lot more detail on that when we get to data path design. But for right now, that's what we mean by that. And the overflow flag. And the carryout flag. So you have A and B. So if you were designing it, you'd say 32, 32. This result value is 32. The 0-bit is 1. The 0 flag is 1 bit. And the overflow flag is 1 bit. And carryout is 1 bit. It looks like everybody's done with 2.12, so I'm going to scroll up past 2.13 to 2.13 here. So this is an example of our truth table for the ALU control input. So when you have 0, 0, 0, 0 as your input, it's going to be A and B. So people have done this TGO in different ways. You can either have an if-else statement. Some people do truth tables. So if you just say input ALU CTRL, then you can have operation. So you could say 0, 0, 0, 0, A and B, 0, 0, 0, 1. It's going to be A or B. 0, 0, 1, 0 is going to be A plus B. In this case, 0, 1, 1, 0 is going to be A minus B. So remember from last lecture, what's important about the fact that the difference between 0, 0, 1, 0 and 0, 1, 1, 0? What's different between these two, and why is that useful? Does anybody remember that from last lecture? The difference between addition and subtraction is 1 bit. What can we use that bit for? No one?
Sign change.
Yes, there we go. That's what I wanted to hear, right? Remember that it's the sign change, right? So you just have the value as the carry in, and then you also have that as your input to your XOR gates, right? So that means that you can, by using this design, making sure that the inputs to the control unit is just this different, you can actually have essentially the same control signal with 1 bit difference, and then you can actually significantly cut down on the area of the ALU. So that's a good example of an advanced digital design. So for this value here, let me zoom in on this just a little so you can see what I'm talking about. So this notation, what this means is if the ALU control is 0, 1, 1, 1, that means that ALU out represents the value of A less than B. And this question mark here means that if A is less than B, the value is 1. And if not, the value is 0. So if this were like 1, 1, 0, 0, A greater than B, question mark, 1, 0. Excuse me. Thank you. That means that the output 1 indicates that this is true, and at 0, this is false. And so the difference is when you get the values of A and B, you're actually getting the actual logic value, right? When you're getting A or B, you're actually getting the actual logic value. Same thing with addition and subtraction. When you have A less than B or A greater than B, as you saw in the previous topical guide objective, you have some sort of bit result that you want. In this case, that's what this indicates. It's not the value that's going to be on the 32 bits. When we get to the data path design, you're going to see that whatever other value comes out when it performs the rest of the calculations doesn't really matter. We just want that 0-bit result. And then else if ALU control equals 1, 1, 0, 0, then the ALU out is going to be equal to the negation of A or B. So just A or B not. And so the actual name for this, I should probably emphasize here. This is known as a set less than. So you'll see this, especially when we get into the design of how we actually compile down to the assembly language. Set less than is you take two values, and if one of them is less than the other, then you set the result register equal to 1. So the set less than is an R-type instruction, because you're taking two register values, performing some sort of operation, and storing the result in the third register. And so this becomes really important because when we have less than or equal to instructions, MIPS only has less than or not less than. So what that means is that you actually have to perform, if you're doing less than or equal to, you have to perform two instructions. Does that make sense? So a common mistake is someone will say less than or equal to some sort of MIPS instruction that doesn't exist, and that's just wrong. So what you do is you do the first operation, you set less than, you store it in a temporary register, and then you take that result and then compare it to the second one, and that gives you your actual less than or equal to or greater than or equal to. And we'll go into that in more detail later. Okay, so this 2.15, this is where we're tying this now into the actual instruction. So recall from the machine instruction, we had the first 6 bits of the opcode, and then we had 5 for the registers, 5 for the second register, 5 for the third register. We had 5 bits for the shift amount, and then we have this 6-bit last value, which is known as the function. You all remember that? So that is actually coming from the actual instruction itself. So this is where what we're learning in the arithmetic logic unit is finally coming into what you were learning previously in the instruction. So in this case, function help you differentiate between R-type instructions and the actual operation that we're performing. So the function here is 6 bits, so it's 2100110. So when you look at the MIP green sheet, it's going to be in hexadecimal. So the first one's going to be a 2, and then this becomes 6. 26 hex is AND. One zero zero one zero one or 25 hex is going to be OR. So what's actually happening is the function is coming into the it's known as the ALU control, and then it's performing an operation where it's giving you the ALU control signal. So this is coming from the actual instruction, and then it's giving you this 4-bit ALU control value, which is then sent to the ALU. Because as we'll learn later on, the ALU controller and the functions perform other operations. So here, add and subtract, it's 20 hex and 21 hex. 20 hex is add, and then, 22 hex is subtract. And function 2A hex or 101010 is going to be set less than, and then 100110 or 27 hex is going to be your NOR operation, because that's going to be ALU control. And so the reason why I set it up this way in these last two topical guide objectives is because if you're doing you're writing up some code in Verilog or VHDL, as you will do in this course and then you will do later in 386. Laying this out this way allows you to actually just go through and just write the code out. So if you're saying, I got to design an ALU controller, I got to design a function, I got to design a control signal, I got to try to design arithmetic logic unit. Well, when you do it this way, you actually can go, all right, well, I got my input here. I know what my inputs are. I know what these values need to be for the decision logic, and then I'll allow my design automation tool to synthesize it down for me. Does that make sense? So this is something that when I started out as an engineer, I found was a very good habit to lay things out like that, either in a table or in some sort of if-else statement. Save you a lot of time in troubleshooting later on. Okay, so right now what we have, we'll go into more detail. So you have some sort of arithmetic logic unit. So you have some A and B input. You have an ALU controller 4-bit value. You have your 32-bit results. And then you have a 0 flag. And then we have our overflow and carryout. And then you saw how to design the arithmetic logic unit. You designed a full adder, you designed a comparator, you designed AND and OR. You've been able to put them together in a multifunctional arithmetic logic unit. And you now know from this 4-bit value that we're going to be getting this ALU controller, we're receiving a 6-bit function value that performs this logic. And so you synthesize this down, you now are getting out to beyond medium scale integration. Now you're getting into large scale integration. So we're almost at VLSI. You can see I'm designing it down that way and then building up as I've demonstrated. You can actually start to design a pretty large circuit. Okay. Does anybody have any questions about this? All right, so now that we're starting to design this ALU, how do we actually use this to perform operations? So the first thing we're going to discuss is this concept of floating point addition. So floating point addition, if you recall from when you're doing a grade school, say you're doing 9.99, if you're doing 9.99 plus 0.16, right? And if you're doing that in school, you know there's something that we're not accounting for over here. You just knew that this is basically 10 to the 1, right? Or this would be 9.99, or this would be 10 to the 0. In this case, it's 10 to the 1. So what we're actually doing is 99.99 plus right. So basically, you're now getting 100.15, which is the same thing as that. So what's actually going on here is I'm emphasizing this concept of carry. So this is a carry bit, or a carry digit, I should say, since here we're actually doing base 10 addition. So what ends up happening is, in order to do this, what you end up doing is you have to do 10015 times 10 to the 2. Or if you have the number of bits, it would be 1.002 times 10 to the 2. If you recall from chemistry or any kind of science course where they got very they're very clear that you had to have a certain number of digits, and if you didn't, they got on your case about it. And sometimes you're probably like, well, why? Why is that important? Well, the reason why is because sometimes there's only a certain number of values you can actually store or know. In the case of chemistry, you can only, it depends on the measurement, the accuracy of the measurements. So you can't have certain, if you only can measure up to 3 digits of precision, you can't have a 4-digit result because you literally can't prove it. In this case, the reason why we do that is because we only have 32 bits in our architecture. So you can't have a 33-bit solution. Does that make sense? In the case of floating point addition, we have a 23-bit mantissa. So once you start getting into the 24th bit, you're actually starting to just lose values because we can't physically represent it. So in this case, what we are going to do is we are going to show some fundamental examples of digits. How do you actually convert it to IEEE 754, and then how do you perform the operation? So we have 3 examples of this. So we have 1 where both of them are positive, and then we have 2 where one of the 2 is negative. And we're going to show you how those differences resulted. So I have switched around the problem order. I've just uploaded it on Blackboard. So for those of you who looked up there and saw that the example questions are in a different order, that's by design, because I looked over the reviews and feedback I got from students, and there was one issue that students were having with understanding how to do negative addition or subtraction using floating points. So I've switched it up to try to help with student understanding. So in this case, what we have is and you're gonna have a question like this on the exam, where it'll be some value between 0 and 1. It'll be 4 digits, and it can be represented with 4 digits of binary precision of a decimal value. It will be no greater than 4. And so in this case, 0.8125, the way you calculate that out is that it's greater than 0.5, so it's a 1. So it's going to be 0.125, 3125, right? It's greater than 0.5, it's not. 0.3125 is greater than 0.25, it is. So that comes out to 0.625, which it is, right? So it's 0.1011, right? Which is what we got here. Same thing with 0.25, that's even easier to convert. So it's 0.0100. So in this case, what we want to do is, if you recall from IEEE 754, our normalizing is we find the first value of 1, and we have that represent the digit, and then everything else is the mantissa. So in this case, the mantissa is represented by these values here. So you would initially be getting in sign bit is 0 for 8.8125. You get 2 negative 1, so it would be actually 127 minus 1, which is 126. So the actual value is going to be this value here. Same thing would be 125. So it'd be 0.111101, right? But in order to add them, we want to make the values the same. So basically what's going to end up happening is you're going to compare the exponents, make them the same, and then take those values and then add them. So then you're taking the 23-bit values and putting them to the adder. So in this case, what's happening is this value You're going to use the bigger value. In this case, it's -1. And then you shift it over like so. So this becomes actually 0.1000 times 2 to the -1. And we're adding those up. So when you add them up, it becomes 10.0010 times 2 to the -1. Now, if you recall from last lecture, where I talked about how you can only have overflow if you have two addition values where the signs are the same, right? So in this case, the signs of the two IEEE 754 results are both 0 because they're both positive. So you can have overflow, which means if you overflow like this, what's going to end up happening is, well, you just shift the bit and you're fine. And the reason we're able to do this is because we are having two 23-bit values that we're adding with a 32-bit adder. So we make the exponents the same. The overflow is actually not really overflow because we still have another 9 bits we can use in the adder. So we can just shift it. We just then tell the arithmetic logic unit to change the exponent. So therefore, what ends up happening is this just becomes 1.0001 times 2 to the 0. So this 0 value, if you recall from IEEE 754 format, is the result of E equals. The exponent is equal to this value minus 127, or 127 minus that value, right? So it should be, right? So E equals minus 127. So then in this case, just E equals 127, right? So that means that the value that we're putting into the IEEE 754 format is going to be 127, which is this value here. So in this case, the mantissa is going to be 0001. Does that make sense? And that's the value that goes here. And since it's positive, that's going to go there. So a valid exam answer is this. Let me scroll up a little bit so you can see. So what's happening here is we've added this up. We shift it over, so it becomes 1.0001 times 2 to the 0. This 0 value is the result of the equation of 0 is equal to E minus 127, which we have from that, if you recall from last lecture, the IEEE 754 format equation. Just solve for E, you get 127. You plug that value in here. So if you recall, the result's going to be either 129, 128, 127, or 126. So it'd be very easy to add and subtract the 8 bits here. So this is 128. So 127 just becomes that. And so on these things, I always like to add a check. You're not required to do this on an exam, but it's always kind of a good idea just to make sure that the number that you're expecting to go into your IEEE format matches what is actually the result. So in this case, this value 0 is there. This value here, when you add it up, becomes 1 plus 0.0625. And then 127 minus 127 comes out to 2 to the 0, which is just 1. So this result becomes 1.0625. And then we check the actual values. 0.8125 plus 0.25 is in fact 1.0625. So we have the right answer. Does that make sense? Does anybody have any questions on this? I'll be happy to discuss again. We're going to go over 2 more examples, but with sign 2's complement in a moment. All right. So example 2.3. So let's start here. I'll leave the solution up there for a moment. So now we have 0.5625 and negative 3.75. So calculating the sum using floating point addition algorithm. Keep 4 bits of precision during calculations and represent the result in IEEE 754 single precision format. So There's not going to be a result where you need to keep more than 4 bits of precision. So recall here the result 0.001 ... mantissa is 23 bits. Because this will be the question where I ask you about IEEE 754. So when you write that result, that means you're demonstrating you know how to do floating point addition, you know how to do the appropriate conversions, and you know that this is an entire 32-bit value. So just doing that demonstrates a lot of knowledge. Okay, so 0.5625 is greater than 0.5, so you subtract that, it just comes out to 0.0625. So it simply comes out to 0.1001. So then we can say that by using how we do IEEE 754, we shift it 1 bit, so you get 1.0010 times 2 to the negative 1. 0.375 becomes 0.0110, so it becomes 1.1000 times 2 to the negative 2. We take the higher bit value, we take the higher exponent value, so this becomes 1.0010 and 1100, and then you perform the 2's complement of that number, of the negative number. So it's going to come out to 1.0100 times 2 to the negative 1, because 0.375 is negative. So then what we're doing here, we're adding these values up. Since the signs are different, the mantissas will be subtracted, which is fine because we've performed the 2's complement. But the key thing is, since they're different, we cannot have an overflow. So what ends up happening is if you're doing subtraction and you get this negative value and the signs are different, that means it's just an extension of the negative number. Oh, I'm sorry, it's an extension, it goes away. It's carried. So in this case, we're adding these values up. We got, you can ignore this portion here. What that actually means is, come on, you can do it. You see how this number is the 2's complement there? So it's 1.0010 times 2 to the negative 1. So we add these values together, now that we've performed the 2's complement. Because the signs are different, you can't have overflow, so this value is ignored. And so the result that we're looking for here is this value, 0.0110 times 2 to the negative 1. Does that make sense? So if you get overflow in some sort of subtraction problem, and we'll see a difference here when we flip the bits and perform the problem with in example 2.4. This means we have a result where there's a subtraction and we have a positive number because of that. So you normalize the result. We go 1.1000 times 2 to the negative 3, because what we've got is 0.0110 times 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. Now that we've found the first one, we can put it into the IEEE 754 format. Since it's 2 to the negative 3 is the result of E minus 127. Therefore, E is going to be 124. So that's going to be 0.111100. And so what happens is we take that value, this result here of the 1.1000, we take that result here into the mantissa. We take that 124 and we put that result here. And then mantissa is 23 bits, and that is a valid exam answer. And then we do our check. It becomes, since the mantissa is 0.1000, it's going to be 1 plus 0.5. We know it's 0 here because we don't have carry bit, because this 0 point result, that's going to be our positive value. Because if you're adding two values that are less than 1, I mean, so if you have a value that's less than 1 and you're subtracting a value that's less than 1, you can't get greater than 1. So that's why we can use this as our sign bit. Does that make sense? So it comes 1 plus 0.5, and then we know it's 124, so it's 2 to the 124 minus 27. So it becomes 1.5 times 2 to the negative 3, so that's 1.5 divided by 8, which actually becomes 0.1875. And then we check the original number, 0.5625 minus 3.375 is in fact 0.1875. Does that make sense? Awesome. So I'm going to scroll up here. So this is going to be a very similar problem, except instead of the 3.75 being negative, we're making 0.5625 negative. And so we should get a negative number as a result here. So what we're going to do is we're going to do the same thing as we did before. 0.5625 is 0.1010. 0.375 is 0.0110. Yep. Now, what we're going to do is we're going to perform the 2's complement of 0.5625, and then we're going to get this result here. Because we got that value, add it, becomes 0.1101, it becomes add 1, 1110, which is how we got this number here. So then we add them together. Now here's what happens. We add them together. We don't have a carry because 0.1110, 0.1101, sorry, 1100, sorry about that. 0, 1, 0, 1, 1. But then this bit, it's here. If we in the previous problem, we got that carry that went past the most significant bit. We had that value come out to 1. So this value came out to 0, so we're good. We don't have to worry about that. This value came out to 1. That means we have ourselves a negative number. So what we do, we're going to perform the 2's complement, and what we're going to actually get is 0. So it's 0.0101. We add 1, 0.0110. Does that look familiar? Because it's actually negative 0.1875. Because basically we're just, you switch them around, you should get the same result except negative. So what we've actually done here is successfully switch the signs, and using our knowledge, we're actually able to perform the 2's complement. So the result is the same thing as the previous problem, except the sign bit is 1. And if you do the check, it's 2 to the negative 1, 1 plus 0.5, 2 to the 124 minus 127, it's going to be negative 1.5 times 2 to the negative 3, which is the same thing as negative 1.5 divided by 8. And as a result, we get negative 0.1875. Does anybody have any questions about how this result here of this 1.1010, which, and if you don't mind if I'm going to scroll up here for a moment, you see here we had this 0.0110. So we took these two values here. We had the 1.1010, and then the second we had 0.110. This here, because it's negative, we perform the 2's complement, so we get 0.0101, 0.110. So that means this is the negative value of 1875, and this is the positive value. Does anybody have any questions about how I did that? The reason I'm asking is because there's going to be an exam question and a potential future quiz question that we will be expected to replicate that. Okay, sounds good. All right, so in that case, now we're going to talk about multiplication and division. So we're going to talk about signed multiplication, and then we're going to have two different types of division involving binary. It's going to be restoring and non-restoring. And the reason I'm presenting two forms of binary division is because it's a good description of how you do trade-offs for area and performance. I think that's a good thing to emphasize at this stage in your career. So what the multiplication and division, if here, basically what we're doing is we're doing an unsigned multiplication of 2 times 3. So the multiplier and the multiplicand become important. So we're going to be actually going over the algorithms. And multiplier is the second value. So you have 2 times 3. It's a multiplier. If you think about it, it's a verb. Multiplier, how many times am I actually doing it? I'm doing 2, and I'm adding 3 times, right? 2 plus 2 plus 2. So it's the multiplier. The multiplicand is what is it that I'm doing the operation on. So in this case, if you're just doing a conventional multiplication, what you're doing is you're just adding this value 4 times because we have a 4-bit value. So it's multiply 2 times the value 1 here, you get 2. Then you do a bit shift. You multiply 2 times 1 and get that value there. Then here you do 0 times 1, then you add that result. This is still 0. Still get that result. So then you're going to have this result, which is going to be 2 times the number. It's going to be 2 times the number of bits minus 1 every time. So here, this comes out to 6 because we're just adding. So the question becomes, how do we create hardware that specifically does this, and how can you improve it? So I'm going to scroll up here and show you the general idea. So when I was doing this problem, this value that I was constantly adding, that value at the bottom where you're going to have the product is what's known as a product register. So if you have a 232-bit ALUs, what we're doing is we're storing it in the 64-bit register, and then we're going to be constantly sending it back. So if you see this value here, what we're doing is the actual value of the register starts out as all zeros, and then what ends up happening is that we go through here and we're just adding. So here we're going to be, if it's 1, we're going to add this value here. We go to the next bit, we shift the multiplier right, and we shift the multiplicand left. So then the multiplicand becomes 0, 0, 1, 0, 0. If it's 1, we add it. So initially the product is 0, 0, 0, 0. And that's going to be 0, 0, 0, 0, 0, 1, 0, right? Because we're adding that because it's multiplying by 1. You shift right, the bit's 1 again. Because we've shifted this value left, it's going to be, we're going to add it. So we're going to 0, 0, 0, 0, 1, 1, 0 because we're adding that shifted value and the previous value in the register. And then the next time we're doing it, we're adding the values, but it's actually 0. So we're not adding anything. So it allows us to go all the way through. It's the same thing as when you're multiplying 14 times 16. You're just adding that value. What you're doing at the bottom with the addition, the computer's doing that for you. So what's going on here is that testing of this 1 bit here is what's represented in the diagram here. We're testing the least significant bit because we're shifting the multiplier right and we're shifting the multiplicand left. So a multiplicand keeps coming in here. Initially, we're using a 32-bit ALU where we have an adder. We're just adding 32 times, and each time we shift right for the multiplier, and then we get our 64-bit result there. Does that make sense? So that's what's physically going on in the advanced digital system. So I kind of just included a very quick note about the Kara-Tsuba algorithm. It's something that so this big O notation I was talking about earlier, when you have to do shift left, add, shift left, add, shift left, add for each one, what you're going to notice is that you're actually performing what's known as, it's one of the big O n squared notation. So whatever the input is, you're actually going to be performing a total of n squared. So if you have 32 bits, it's going to be 32 times 32. If it's 8 bits, 8 times 8. So then big O of log 2 of 3 is less than 2, so this is the fastest known multiplier algorithm. However, it's very difficult to implement in hardware. It requires a lot of area, a lot of power, a lot of time, high cost, and not really that much performance benefit. So even though theoretically they know how to do it, it doesn't really do you much good. So sometimes you just want to look for sign multiplication algorithms that will perform all these for you. And so in this case with sign, you have to worry about the most significant bit being, so you actually can multiply 31-bit values, and you have to worry about the sign. Performing the operations overwrites the sign bit, so it's the same thing where we have these 64-bit values. So you have to worry about n plus 1 bits of space. So that's a fancy way of saying that if we're multiplying, since we have data path which is 32 bits, that means that we only want to have 31 bits that we're going to multiply in a sign bit, so that there's no way that we'll overwrite all the values in the 64-bit product register. So this is the actual sign multiplication algorithm. So what's going on here is if you were to write a multiplier, you would take in, you know that the number of bits is n. Now the reason I have it this way, even though it'd be very easy to just write multiplier is 33 bits, multiplicand is 65 bits because it's 2n plus 1. When you're actually writing code in Verilog and VHDL, you can actually define a global variable that indicates the number of bits of your architecture. So if you were saying, I want to do a 16-bit architecture, I would just do n equals 16. Instead of having to go through and write all of your code and rewrite 32 and rewrite 32 and change the integers, you can do it more simply by just using this notation and then changing one value in your code. And then you can use the synthesis tool to do a lot of the area and power optimizations for you. So in this case, in algorithm notation, all of these values are going to be your inputs and outputs. So we want to have a multiplier of 33 bits, a multiplicand of 2n plus 1, because we're going to be storing that value in the result. So that we have the inputs and the output product. So what we're going to do is this first value here, the product of 2n, which means we're getting the value that goes into the most significant bit, because as for those of you, I think most of you have done some sort of coding class, we all aware that the first value of array is 0. So 2n is going to actually be the 2n plus 1 value. It's the most significant bit. So product of 2n is equal to the XOR of the multiplier and the multiplicand. So it's the most significant bit of each of those values. So basically what we're figuring out is our result going to be a positive or negative result? And so next we're going to be iterating through our algorithm for I equals 0 to n. So the results we're going to be doing it n plus 1 times. So 0, 1, 2, 3, 4, 5. If we're doing 16. That means we have 17 iterations. If it's our 32-bit MIPS register, we're going to have 33 iterations. So if the multiplier is equal to 0, if the multiplier of the least significant bit or the multiplier of the 0th bit is 1, that means we're multiplying by 1, right? So we're going to multiply that value by 1. We're going to add it and store it in the product register, which goes on here. So the same thing earlier on. That's our testing of our least significant bit. And then we're multiplying by 1. And then we're going to add it to the product, right? So the product register is 0. We're adding this multiplicand. So we're going to shift the multiplicand left 1 bit like we did in the diagram. And we're going to shift the multiplier right 1 bit like we did in the diagram. And at the end, we return the product. So we're going to go over 2 examples of this momentarily. Now, I think I've done a better job of describing. I'm going to scroll up to the. Okay, nah. this is for detail, but I'll describe what you don't have to write on an exam here in a moment. All right, does anybody have any questions before I move on to the problem? All right, so what we are doing here in example 2.5 is we're multiplying 8 times negative 9 using sign multiplication. So in this case, and on the exam, you may assume that n is equal to 4. I will not give you a problem that cannot be represented by more than 4 bits. So I also want to emphasize here before we move on, before you guys start writing stuff down, you only have to write the first time that the value comes out, right? So if you see all these values where here I have, you don't need to write this. You only need to write the first time it changes. Does that make sense? So you can just leave all those blank, and the moment it changes, you just write it once. I'm only including it here on the lecture notes for the sake of you actually understanding and being able to point out here that when you're doing the shift, that's where the shift is. So you actually physically see the stage where it occurs. But you don't have to write that on an exam. You do not need to write it 8 times. That's a waste of your time, right? We have a question? All right. Yes. Oh, sorry. I thought you had a question. All right, no, we'll walk through this all in a second. It's okay. I understand it gets... We'll just start here. So step 1, step 0 is initialize, right? So remember that first step. We're getting in our values, and we perform that XOR. Okay? So what we want to have is 9 is 1001. So we're going to perform a 2's complement of that value. So that's our multiplier, 8 times negative 9. The multiplier is the second value, the value that we're actually using. Whereas the multiplicand is 8 in this case. So the multiplier is going to be 0111 like there. And then it's going to have a negative value there to indicate to indicate there's a negative number, which is why in the algorithm it says n plus 1 bits. So here the multiplicand is going to have 8 or positive 8, and then the most significant bit is going to be 0. So the first stage here, and basically most of the things that you need to write are in red, as opposed to all the rest of it's in black. But here, that most significant bit is changed to a 1. That's the XOR. So that's the first thing you need to indicate. So from there, we're going to test the multiplier. So in this case, you don't need to write that out. What you're doing, you don't need to write out this value here. Don't need to write it. But the testing the least significant bit means that we're actually looking at it. And since it's a 1, we're actually going to add the multiplicand to the product. So here, add multiplicand. So now this result is 1, 0, 0, 0, 0, 1, 0, 0, 0, because we're adding 8. So then we do the shift left of the multiplicand and shift right of the multiplier. So what's going to happen here, you can, what you're going to do is you're adding a 1 here because it's a negative number. But what's actually going on here is these values are now being shifted over. So you see that these 4 values here are now these 4 values here. So we're shifting right. And then we're shifting right on the multiplier. So you can see that these 4 values, we're shifting left on the multiplier. Shifting left on the multiplicand. So those 4 values become those 5 values there. And then rinse and repeat. If it's a 1, we're going to add. So in this case, once again, we have a 1. So now what we're going to do is we're going to add the multiplicand to this value here. So you can see now that this is 8. So now we're adding 16 because we multiply it by shifting left. What we've done is multiply by 2. So this becomes 8 plus 16, which is now 24. And since we have a negative number, we're now representing negative 24. Ultimately, we want to get to is negative 72. Shift left, shift right. You can see it here once again that this has been shifted. So now these 3 values are now these 3 values. So you're just adding these ones here as placeholders. If it's a positive value, you add zeros, as you'll see in the next example. But because of the number of iterations in the algorithm, we'll never go past these 3 anyway. So we get to stage 4. We are now adding, testing the multiplier is 1. We're going to shift left. We got to add. So now, once again, we got here. So now we're adding 32 plus 24. And then we shift left and shift right, shift left, shift right. So now these 2 values are the values we're worried about. Here, stage 4, we're testing is the 0, so you don't need to add at all. So you don't worry about it. Just shift left and shift right. And then finally, we have a 1. So now we are actually adding this value here and getting our result. And so instead of taking the last 3 minutes to go over this other example, we'll just stop here for now. We'll stop at this example. I'll post the video and send you the lecture notes. Does anybody have any questions on this before I dismiss you? Everyone's like, no, I just want to get out of here. All right.